Great. Okay, so hi everybody. Thank you so much for joining us for this SEDS Online webinar. My name is Chelsea Pedersen, if we haven't been able to meet before. And before we get started with today's talk by Elizabeth Steele, we'd just like to thank our sponsorship from the IAS, which allows us to offer all of these SEDS Online resources to you free of charge. Make sure and check out the website for everything that we have available. All of our webinars are recorded, all of the great debates that hopefully you've been able to check into. It's all there ready for your viewing pleasure. So take a look at the website and see all of that new info. Today, we also hit our 1,400th subscriber, Vimal Singh. So yay, Vimal, thanks for joining us and for hitting that mark. So we're really excited to be able to continue progressing and sharing all of these resources for the community. And today's lecture, as I mentioned, is by Dr. Elizabeth Steele, who's an assistant professor at Queen's University. And Elizabeth received her PhD from the University of California, Santa Barbara, before heading to the University of Minnesota for her postdoc. Her research focuses on understanding transport processes and sediment gravity flows and how they shape terrestrial and marine environments. Today, she's going to talk to us about how to sort of link the morphodynamics with stratigraphic connectivity. And with that, Elizabeth, I will give you the mic.
All right, thanks, Chelsea. Thanks everyone for being here and thanks for the invitation to give this talk. I'm looking forward to talking to you all about some work that really started when I was a postdoc at St. Anthony Falls and is continuing. And it's part of a bigger collaborative project with colleagues at University of Minnesota and University of Texas in Austin and the University of Delaware. And we're really interested in trying to understand the linkages between what's going on in surface networks of deltaic systems and how we can sort of use that information to better understand subsurface architecture. So today I'll be talking mostly about an experimental data set that we use to try to develop a method for using surface imagery, time series of surface imagery to build what we call synthetic stratigraphy, or to sort of recreate stratigraphy. And what you're looking at on this title slide is a photo of stratigraphy that was built from an experimental delta. It's a couple of meters deep at its thickest and about 6 meters long. And this is sort of a back tilted delta. So the thickest subsidence is up here. This is the proximal part of the delta, and we're basinward off to the right. And hopefully you can see some of these foresets building out through sea level. So we'll be talking about this a little bit more in a little bit more detail. But I just want to start with some general motivation for this work. So in general, what we were interested in better understanding was what controls fast transport pathways of contaminants in groundwater reservoirs, and specifically in deltaic settings. So if we think about our deltaic surface environment, we have these rivers and distributary channels that serve as conduits for water and sediment on the surface. And as these channels move around and build land, those networks get translated into this complex three-dimensional plumbing network that becomes the conduits for groundwater and for potential contaminants as well. And so if we kind of simplify this idea into having sort of coarse-grained channel bodies and finer-grained overbank and floodplain sediments, we can understand that if we look at these two cartoons on the right, whether the channels are organized in the way that you see in the top panel, where they're fairly isolated from one another, we'll have really different vertical and lateral flow connectivity patterns compared to this bottom cartoon, where a lot of these channel sands are well connected and you might be able to have sort of transport of contaminants. So on the Google Earth image here, I'm showing you the Ganges Brahmaputra Meghna Delta in Bangladesh. And this is an example of a delta that has a really large population of people that rely on a solid understanding of how connected the sands are in the subsurface for their groundwater resources. And the main contaminants in this area are things like arsenic and salt water. And in general, if they are able to drill deeper wells, there are lower levels of contaminants in this region. But there are occasional places where they have these really fast vertical flow pathways that allow for drawdown of contaminants into those deeper wells. And so this is kind of the context that we better want to understand. How can we sort of predict the architecture of these environments? So a useful tool for trying to understand how we can connect surface processes to the subsurface is to use experimental deltas. So I'm showing you here a time lapse of an experimental delta that was primarily run by Liz Hayjack when she was at St. Anthony Falls in 2010. So this is the Jurassic tank, or the experimental earthscape basin. It's about 3 meters across and 6 meters long. And this experiment ran for 310 hours. And photos were taken of the surface of this delta every 10 seconds. So we have a huge amount of imagery of the surface. And we also have topographic scans that were taken about every 4 hours. And as you may be noticing, this delta also experienced several sea level cycles. And we'll talk about that a little bit more. And then again, there was sort of maximum subsidence in the proximal reaches of the delta because they were trying to model back tilted subsidence. So the basin floor in this flume can subside as well. So we're going to use this data set for sort of the stuff I'll be walking you through today. And we can use this to sort of answer the question of whether we can use surface information, like for example, whether we can take photos which are abundant, paired with some scans which we have but are less frequent, and whether we can use that to try to understand the kind of large scale stratigraphic architecture of a system. And we're going to build what we're going to call synthetic stratigraphy. So in order to predict stratigraphy, if we want to take a really simplified view and think, okay, we're just going to assume we have sand bodies deposited by channels and finer grain sediment outside of our channels, then the two kind of key pieces of information we need to know are the locations of channels through time, and also the bathymetry, which will tell us about whether or not these channels are able to vertically connect or laterally connect to one another when they're near each other. And building synthetic stratigraphy is not necessarily a new concept. So this is something that experimental sedimentologists have done quite a lot of. And one way that people have done this in the past is just by taking topographic profiles throughout an experiment and sort of stacking those profiles together through time and allowing them to erode each other. So this is a pretty nice example from Kyle Straub and Brady Foreman, where they built synthetic stratigraphy from a delta. And you can see kind of places where these channels were eroding into underlying stratigraphy. But one thing that one sort of key piece of information is that imagery is much more readily available than topographic data, both in natural systems and also in experimental settings as well, where it's much easier for us to take photos of the surface through time than it is to pause and take topographic scans. And so we wanted to ask the question of whether we could use this imagery to our advantage to either fill in some of the gaps between topographic scans or still build synthetic stratigraphy if we might have a pretty large absence of topographic information. So as I mentioned, we kind of need to know two things. We need to know channel location and bathymetry. And channel location is a pretty easy one to get when we have imagery, especially in experimental imagery. So here what I'm showing you is a color image of one time in this delta's evolution. And normally what people will do is they'll take maybe just a color band and grayscale it and use like a threshold on a color band. So in this image, we might use red since that's the opposite of this cyan color here. But what we found in this experiment, and I imagine others probably struggle with as well, is that we have this mixture of sand and coal as the sediment source. And the coal was being kind of incorrectly classified as water. And so we were sort of not getting very accurate land water maps from just thresholding. So what we did is we took the red, green, and blue color bands and put it into principal components analysis. And when we do that, we get 3 principal components from these maps. The first one you can see does a pretty nice job of highlighting differences in the land contrast. So we have it's really picking up actually and responding really strongly to those coal layers on the surface. So it picks up some of the water, but this is mostly looking at variance in land surface. Our second principal component did a really nice job of identifying water from dry land. So this is actually the data set that we're going to use to kind of extract all of our channel networks from the imagery. And then as you can see, the third principal component is just not that useful. It doesn't pick up a lot of variance. So we use this PC2 image, the second principal component, and we can sort of provide a threshold value where we say, okay, sort of below this value, we're in the channel, and above it, we're outside of a channel. So that's finding the channel networks, but the channel bathymetry or the channel depth is much more difficult to do from imagery. Predicting bathymetry from images is not very straightforward. And what we did was, well, actually what Hannah Bramacher did, who's currently a master's student, but at the time was an honors thesis student, pulled the topographic scans into QGIS. So we had about 123 of those, and she found photos that corresponded to the timing of the scans and overlaid them so that we could get information about the bathymetry of the channels and then also measure things from the imagery, like the pixel color or the width of the channel and things like that. It's really actually still quite difficult to build relationships between things like the color of the pixels and the channel depth because things get saturated pretty quickly. But what we do have from that is a pretty good database of channel depths and corresponding widths of channels to those depths. So we're going to use that to try to estimate channel depth in kind of a really crude sort of way. So what we have here is a histogram of the channel depths that were measured in our experiment. What we can do is we can take this distribution and we can put it into a cumulative frequency distribution. And so the CDF ranges from 0 to 1, and it spans our channel depth ranges. So what we can do is what's called essentially an inverse CDF method, kind of like Monte Carlo method, and we can use a random number generator, which you can find in really any kind of software, computer software, and have a random number generator select a value between 0 and 1. So let's say we have located a channel and we want to just sort of randomly draw channel depth from it. Our random number generator can give us a value of 0.4, for example. So we would then randomly assign that channel a depth corresponding to that value, which would maybe be about 4.5 millimeters deep. So this would be one way that we can just sort of draw from a known distribution of populations in a way that is sort of statistically reasonable. But we can actually do better than this. So this is just all of the channel depths that we've measured in our experiment, but we do know some information from the photos, and it turns out one of the more useful pieces of information is just the width of the channel. So intuitively, we can know that wider channels are more likely to be deeper, and that is what we see in the data set that Hannah collected, where we can break up our channels into sort of narrow channels, medium, and wide channels. And these are the CDFs for all of those different channel widths. So you can see here now, if our random number generator were to give us 0.4, if it was a narrow channel, if we looked at the image and knew it was within the narrow range, we would give it a depth of maybe 2.5 millimeters. Whereas if it's a wide channel depth, we could give it a depth closer to 7 millimeters, for example. So this is a way that using just the imagery and a little bit of information about what the topography, what a reasonable topography of the system is like, we can locate our channels and sort of estimate a reasonable depth for those channels. So we kind of get into building the synthetic stratigraphy. So the first step for building the stratigraphy would be to basically start with the first image in your experiment and define a line of cross-section that you're interested in building stratigraphy along. So for example, I picked a pretty simple image for this example. We've got just a single thread river here with a line of cross-section. And we're just going to generate a really simple topographic profile where we essentially just have a floodplain, and then we have our channel. This channel depth is drawn from that distribution that I mentioned before, and then we go back to floodplain. We have some information about aggregation rates in the system. So what we're going to do is go through each photo and do the same thing, find the channels, give them depths, and then subside them based on the aggregation rates. And we're going to allow them to erode into any underlying surfaces that we've already created. So here I'm showing you an example where we start to stack these profiles together for each photo as we move through the experiment. I've been doing it with photos every 10 minutes. That seems to be kind of a reasonable spacing of photos for our data set. And so what you can see is it starts to get really complicated really fast. You can see these channels are really mobile. They're moving all over the place, eroding into each other a lot. So each one of these lines here, you can think of as a topographic profile that then is allowed to erode into underlying profiles. And so you start to get these kind of complicated and composite profiles, which represent sort of multiple erosional episodes, which is not unlike what happens when we see a channel surface and outcrop that we see they're sort of the result of multiple erosional episodes often. So this is the basic method for building synthetic stratigraphy. And what we can do is do that for all of the photos throughout the whole 310-hour experiment. We also have we sort of decided to turn it into more of a rasterized black and white image because that's a little bit easier to work with. And so that's what you're looking at here. So this is just an example of what this synthetic stratigraphy code will do if we define a line of cross-section, for example, here, and we feed this series of images into it, and we end up with something that looks like this. So this is quite vertically exaggerated, but what you're looking at is a cross-section where white represents the channel fill, and black represents basically floodplain sediment that survived reworking. So I should say that this code is a Python code. The paper for this is currently in review, and I thought I was going to get this up on GitHub before this talk, but I did not. But it will be publicly available soon. But you're always welcome to reach out to me if you want to see it sooner. But hopefully this paper will be published and the code will be available, publicly available soon, because I'm hoping that this will be sort of able to be broadly utilized with, especially with experimental imagery, but also hopefully with natural imagery as well. So anyway, we have these stratigraphic panels, and we can choose where we want them to be, and we can sort of see where there essentially is just sand and not sand in this kind of simplified view. And one thing, kind of the main thing that I'd like to point out is that we actually do a pretty good job of characterizing the large scale structure within these deltaic sediments. So here I'm showing you two different stratigraphic panels, one in a more proximal region and one in a more distal region. And if we look at this proximal one, you can see that it develops a thicker sedimentary package because it's in a region where there's higher subsidence, so it's accumulating more sediments. And we can also see places where the stratigraphy is entirely white, suggesting that this is all sand. What this means is that this is basically a chunk of stratigraphy that has been entirely reworked by the channels. This is a very sandy, non-cohesive experiment. This is most sort of directly related to kind of bedload dominated, braided river networks where the channels are extremely mobile. There's very little bank stability. And you can see even from the photos that this is a very sandy system. So it's not unreasonable to think that we might just have this much sand in some places. We also see places though where there's really not been much reworking, and that floodplain sediment has managed to sort of survive being cannibalized by all of these rivers that are moving across the surface. If we look at this more distal synthetic stratigraphy package, you can see that there are some places where we have these big black bands that cut across the entire section. And this is because sometimes the delta surface goes below sea level. So what we do is we kind of mask the shoreline when we're doing the code. And what that means is that essentially anything that's subaqueous just gets classified as not sand, essentially. And so we end up with these big black bands related to when a given location would be receiving subaqueous sediment. And so that's what you're seeing. And for that reason, we're going to start to break up some of the packages into different sea level cycles so that we kind of avoid misinterpreting some of our subaqueous sediment. But for the most part, what we're really interested in characterizing are these topset deposits. So what I'm showing you here are just some more examples of the stratigraphy. So this looks a little bit complicated, but essentially I'll just walk you through it. So this is an overhead image of the delta again, and we're looking at cross-section panels located as line labeled B. So here is the synthetic stratigraphy for that location. And then this kind of splotchy image that you're seeing is essentially the real stratigraphy from the delta. So after this experiment was conducted, they sliced the deposits to look at the stratigraphy, but they actually sliced it in a dip orientation. So all of the slices are like the ones you saw on my title slide, where the stratigraphy is sort of dip oriented, so perpendicular to this section that we're looking at here. So what they did was they basically created composite strike oriented sections by taking all of those dip sections and sort of taking little sections of them and compiling them together. So that's why it looks a little bit pixelated and a little bit blurry. but for our purposes, it helps us do a little bit of a check on whether our synthetic stratigraphy even remotely resembles what the actual stratigraphy looked like. So that's what I'm showing you here. And then these two are just the exact same panels, but with a little bit of interpretation on them. So here we can see we've got these black bands, which would represent subaqueous deposition. And when we look at the real stratigraphy, we can see some evidence of foresets here. This might be a little bit, I've spent a lot of time looking at these, so I'm not sure how clear that is to people who are not used to looking at it, but hopefully you can believe me that we've got some foreset stratigraphy here and also up in this section kind of representing delta front or subaqueous deposition. So here I've basically sort of marked those out. So on a first level, we get those right, which is good. We're kind of accurately mapping out topset versus foreset stratigraphy. And then I think we also see pretty well that there are sections where we do a pretty good rough estimate of sort of sand versus mud content in the subsurface. There are even places where we've got these kind of bigger muddy lenses that make it into the synthetic stratigraphy as well. So we feel pretty confident that the large scale structure is fairly well characterized. Some places where there are some differences between the synthetic stratigraphy and the actual stratigraphy, I think come from that we don't have a way in our code to add in mud-filled channels. So there are some kind of coal-filled channels, and I think that's responsible for some of these darker patches that we don't necessarily see in our stratigraphy. So I want to kind of step back and remind you that what we did was kind of a like worst case estimate scenario where we just randomly drew the depth for every channel. We did condition it based on the width of the channel, but beyond that, we just randomly drew from a distribution of depths. So we wanted to explore how well that random depth draw really, how much that random depth draw really changes the large architecture of these deposits, because we don't want to be kind of just randomly assigning channels that don't make any sense. And so what I'm showing you here are 3 different iterations of cross sections from the same location. So we actually did this for every location. We ran the synthetic stratigraphy 100 times. So in each of those iterations, the channels are redrawn in this kind of random method. So you'll see that there are some very subtle differences between these panels, but overall, it's pretty hard to find really clear differences where you might say, okay, the depth draw in this situation is drastically changing the structure of the subsurface. And this is really good news for us because the channel depth is the thing we have sort of the least information about, but it turns out that the channel depth is not the thing that actually matters the most. What matters the most is understanding kind of where the channels are going through time. And so that really kind of points us towards the fact that kinematics, channel kinematics on the surface is really kind of key to understanding the structure in the subsurface. So I already said this, but essentially what I'm saying is that the large scale structure seems to be controlled primarily by channel location and is not particularly sensitive to really accurate estimates in channel depth, which is great news for us. So we can be a little bit more quantitative about sort of how these channel depths change things and just in general how the structure looks. So we're going to start by just calculating connectivity. So the connectivity is just the largest geobody area. So a geobody in this case, we're considering as a connected sand body, a connected sand package. So we're calculating the largest connected sand package divided by the sum of all of the sand pixels in the section. So you can think of this as if the connectivity value is 1, it means all of the sand in that cross section is connected to all of the other sand. And if you have low connectivity values, you would have a lot of little isolated sand bodies. And because we've got these big zones where sea level is affecting things and probably causing essentially changes in connectivity that are exclusively associated with just whether things are above or below sea level, we're going to break up these cross sections now into just individual chunks associated with sea level phases. So what I'm showing you in the bottom left here is a sea level curve from the experiment. So you can see that this experiment had a constant sea level phase. It then underwent a slow fall and rise, followed by a rapid fall and rise. And then what they did is they did this kind of slow fall and rise with these superposed higher frequency cycles on them. So we're just going to break the stratigraphy into these individual sea level phases to look more closely. And what you'll notice is that I'm really just going to end up focusing on some of these longer time chunks because the other ones didn't really produce enough stratigraphy to say much meaningful about them. And then some of these phases are actually net degradational. Like for example, this rapid sea level fall didn't build any stratigraphy, it actually just eroded stratigraphy. So we are not going to be able to look at anything from that sea level phase. So I'm going to walk you through what these plots are as well. But the main takeaway is things are extremely connected in the system, which you probably already knew just intuitively from looking at these panels. So what I'm showing you here again is that same sea level curve with some of the phases numbered so that you can keep track of where we are in the sea level curve. And on this slide, we're just looking at sea level phase 1. So this is just constant sea level early on in the experiment. If we look at the stratigraphy that was built during this early sea level phase in a specific location, like for example here where I have labeled A to A prime, this is basically the stratigraphy that was built during that time. And then what I'm showing you in this box plot is the sand connectivity on the y-axis, and the x-axis here is downstream distance. So we created synthetic stratigraphy every 12.5 centimeters downstream. And remember that each of these locations, we actually did it 100 times just to sort of avoid any like wild changes that may have happened from changing the depth draw, for example. So each of these box plots, you're looking at one given location, 100 different iterations of the stratigraphy, and then sort of the range and sand connectivity that those have. And so the first thing hopefully you've noticed is that everything is really highly connected. Almost everything is very close to 1, and sort of everything is above 0.96. So 96% of the sand is all connected in the subsurface here. So what we're going to look at now are a few more phases of sea level. So one of the things we find when we do this for each sea level phase, and here I'm just showing you the first one, and then the rapid sea level rise 6 and the rapid rise, which is phase 9. So what we find is that the connectivity is more variable under rapid sea level rise. So here's that plot you were just looking at. Again, the x-axis is moving downstream, and then the box plot shows you essentially sort of the spread in the boxes tells you about how much variability there is between iterations. So essentially how much the depth draw is changing things, and then sort of how that's moving downstream. So we see that not only is there slightly lower connectivity in the rapid rise phases, but also there's a broader spread in the boxes, meaning that it's a little bit more sensitive to our depth draw, whether things are connected or not connected. And I think this makes sense because during these rapid sea level rises, we basically are having more aggradation on our delta top. So when we have more aggradation, likely we're having more sort of channel backfilling and avulsion on the delta plane. And when these channels are avulsing to new areas, their ability to connect to other sand bodies below relies on their ability to erode through the floodplain sediments and into underlying sand. And so it seems reasonable to think that during these sort of higher aggradation periods, we might have these sort of more tenuous connections between sand bodies. But again, we're still talking about things that are more almost, 90% connected or more. So these changes in connectivity, although they're interesting, they're not necessarily going to be changing in any big way the sort of flow structure in the subsurface because everything is so highly connected in this system. So for that reason, we're going to shift away from our sand body connectivity. We're going to start to think about the barriers. So if you look at this panel again, as you can see, everything is pretty highly connected. You could probably draw a line from the bottom to the top quite easily and through all of this sand. And so what starts to become important are these black barriers to flow. You can imagine that if we've got a lot of little isolated barriers, they're not such a big deal. Flow can sort of move around those, especially when we start to think about this in a three-dimensional sense. But when we start to have these broader barriers that span farther across the width of the delta, we start to do things like increase the tortuosity of the flow and sort of cause changes to the transport of solutes in the subsurface. Oh, I added this at the last minute and I forgot. I'm sorry, I'm going to back up for a second. So we see these rapid sea level rises having sort of slightly lower connectivity and also more variability. This is from a paper by Jay Hariharan, who was just accepted and should be out hopefully shortly. But what this plot is showing you here is just PDFs of the connectivity of sand packages run with delta RCM, which is a sort of numerically modeled delta. And so I just wanted to draw your attention to the fact that he sees similar results, which is that under sea level rise rates that are high, like the highest sea level rates here, they have it in this pink dash line and this gray line, show lower connectivity, and the lower sea level rise rates have higher connectivity. So they seem to be seeing a similar story in their numerically modeled delta. Okay, now we're going to talk about barriers. So I'm showing you basically the widths of barriers through all of these different sea level rises. So again, here's the sea level curve if you sort of forget where you are in that. So the y-axis here is just sort of a normalized width. It's just the width of the barrier relative to the width of the cross sections. All the cross sections are the same width. So essentially you can just think of this as a W of 0.5 means that barrier spans across 50% of the width of the delta, essentially. And again, we're looking downstream. And again, this is showing sort of 100 iterations at each of these locations. So one thing we can see is that most of the barriers stay generally below about 30% of the width of the delta. And then in really almost all of the phases, we see this decrease in barrier width downstream. So we see that the barriers are starting to get dissected downstream. I think one of the reasons for this is that as we are in the most proximal reaches of the delta, we really have kind of a fixed apex in this experiment. And so it limits really the mobility of that river in the most proximal sections. And so as we move downstream, we not only have more mobile channels, but we're starting to have bifurcations of these channels. So we just have more of them as well. And they're sort of moving around and reworking material, which results in more dissected barriers downstream. We also see that the slow sea level rise has slightly wider barriers, which is kind of interesting. So in general, I think we see this decrease, but I want to kind of focus on like what this really means in terms of like why barrier width might matter. So here what I'm showing you is just from sea level phase 1 again, so just constant sea level. And we're looking at two different locations. We're looking at 125 centimeters downstream and 200 centimeters downstream. So that's what these two panels are. And you can see the barrier width is decreasing in this box plot. And you can see that visually in these panels where in the upstream section, we've got this fairly wide barrier that seems to have survived reworking. And in the downstream section, we've got more like little isolated barriers. And while sort of initially it seems like, oh, maybe this is good because we've got all this sand over here, in terms of sort of constraining this like element of surprise, if you're drilling somewhere and you're looking for fluid, like you want a clear flow pathway, really these little barriers, especially in 3D, are not going to be creating as many sort of issues for flow as something big like this. And so really these smaller barriers are preferable. One thing that's kind of interesting is that if we look at just the sand fraction between these two locations, so this is net to gross, or basically the ratio of sand to sort of total sediment, we can see that the sand fraction actually isn't changing much between these two. So there isn't really a change in how much mud versus sand there is. There's just a change in how the mud versus the sand is distributed. And so it's not just sort of a function of changing sand content downstream. And so I think what we're seeing is basically that if we are in places where we have potentially more fixed river networks, like for example, if we even think back to the Ganges-Brahmaputra system, the confluence of the Ganges and the Jamuna River is kind of a fixed confluence, or at least it has been. And so we might, in those locations, see sort of less channel mobility, wider barriers, which are sort of potential bigger issues to flow pathways. So I kind of just want to wrap up here, thinking about sort of the original question we asked, which was whether we can use surface information to kind of glean anything about subsurface structure. And I think I have a couple of broad points, which is that we seem to be able to use overhead imagery to constrain lateral and vertical channel connectivity, and also some information about the barriers in the subsurface. And sort of what this means is that our large scale architecture is not particularly sensitive to exact local depth measurements in these channel networks. A little bit more specifically, we find that during rapid sea level rise, we have a greater uncertainty in sand connectivity and potentially slightly lower connectivity overall. And then we see that sort of overbank deposits are likely to be wider and more effective barriers to fluid flow in proximal reaches of deltas or in places where you have fixed confluences, for example. So I kind of wanted to finish with the question of kinematics. I've been talking a lot about how we need to understand delta kinematics, and you may have noticed that I didn't even really have to think about kinematics to do this because we had such frequent imagery. We have images every 10 seconds through this whole experiment. And so we know where the channels are at every step. And that's not always the case, especially not in natural systems. And so kind of the next step is to start to think, well, we know kinematics are important, so how can we sort of use that to incorporate that into sort of some of these workflows? And Austin Chadwick has been kind of leading a really great sort of component of this work where he's been developing methods using PIV or particle image velocimetry to track channel migration through time. And not only is he able to sort of get a whole vector field of how these channels are moving across the surface using this new tool, he's also working now on ways to distinguish lateral migration, so kind of slow continuous migration, from avulsion, which is going to be a really important part of the kinematic step. So here's just a little time-lapse video showing some of his vector fields that he's been mapping in some of this imagery. And so that's currently in review and will hopefully be out sometime in the next 6 months or so. Review processes are a little slow now. So the next steps are sort of to combine what Austin's been working on with some of the synthetic stratigraphy to broaden the picture a little bit and make it a little bit more broadly applicable. So I just wanted to kind of end by saying that this is a code that's in Python 3. I'm relatively new to coding, so if I share this with you, please do not judge me if it is a disaster, but it seems to work, so I'm open to input. But it's going to be publicly available soon, but you're welcome to reach out to me if you're interested in kind of getting a version of it earlier. And so we have a whole kind of slew of papers that are either in review or accepted, and so hopefully we can get those up on Earth Archive shortly so that they'll be available. But I'm happy to answer any questions that you might have. And yeah, just interested to hear thoughts in general. Thanks.
Great presentation. Thank you so much. I personally really enjoyed it. I hope everybody in the audience did as well. So as you can see in the chat, you can now start typing your questions for Elizabeth into that chat, and I can read them out to her as they come through. So I will start us off. A little bit out of my playing field, let's say, but so I just had a quick question about some of the conclusions that you can make using your data sets about the different sedimentological features and the connectivity, basically how it's based or it's determined at least in part by sea level rise, right? So do you think that some of the conclusions that you guys have made so far, is that more tied to sort of a local or regional setting, or can you also make sort of more global determinations or conclusions about these types of structures?
Yeah, that's a good question. So I think one thing to keep in mind is that we are able to sort of suggest that this is mostly driven by sea level rise and changes in aggradation associated with that. So it could also potentially be subsidence in those places of higher subsidence. And part of the reason is because we know in this experiment that our sedimentation, our sediment flux didn't really change and our water flux didn't change. So those things were held constant. Those obviously will also change kind of the kinematics of the system as well and what's going on. But I think that still it is an important piece of the puzzle that can be sort of kept in mind in a bigger picture. the other thing I'll say is that sort of in the most direct sense, this seems to be most related to bed load dominated systems, like really kind of coarse-grained, low bank cohesion systems. But I think that I'm actually really interested in trying some of this out on a sort of less mobile system. I think that because things are so mobile, like the changes we're seeing are really small because everything is just like sand everywhere. And so I think I'd like to think that we would see similar trends in more cohesive systems that might be more clear or more exaggerated when we don't just have like channels all over the place all the time.
Sure, that makes sense. So do you guys have any plans to sort of test this in a more, let's say, muddy system?
Yeah, so I have a master's student currently who is going to be building a delta in our lab here. We're trying to build basically a more cohesive delta, thanks to many people in the community who've given us some advice on that. And yeah, so that is in the works, is to sort of apply some of this to a more cohesive setting and see if we can get that, especially I think with the new PIV method that Austin's been working on. I think that's going to be really powerful for sort of tracking channel movement in a really like sort of three-dimensional vector field.
Yeah, definitely. Okay, so we have some questions in the chat, so I'll cut mine off for now, but we can come back to them in a minute maybe. And so our first question is from Jean Ranke. Hi, Jean. Stimulating presentation. You hinted at using real-world remote sensing time series, but in siliciclastic systems with all the turbid waters, you can't generate depths from optical imagery. Yet that seems an important parameter for generating the synthetic stratigraphy. Can you comment on how you might get around this for real-world imagery?
Yeah, that's a great question. I think there are a lot of, there will definitely be some challenges to sort of shifting this into the remote sensing world, into natural systems. There's a reason why we started in the experimental world, because if we can't do it here, then we definitely can't do it in the real world. But I think that, I mean, that is like that, even in experimental settings, like getting the bathymetric data was pretty time consuming, longer than you would think. So I think what we would have to do, I think we do have some sense of like width to depth ratios in natural channel systems. And so that was another reason why we decided to go with sort of conditional probability using width in these experiments, because width is something that is relatively measurable in most systems. So I think we would just have to sort of use I think if we have some database of our compilation of basically the bathymetric data that we do have for global rivers, with maybe some information about whether they're like sandy or gravel bedded rivers, and then potentially sort of the width of the river, I think there is some possibility. I mean, I think the fact that we can be actually pretty wrong about the depth and still like get some information is promising. Actually on this is maybe a little bit too much to explain, but what we did was we took our depth distribution from the experiment and we just made them like way worse. Like we extended the depth distribution so that we were sort of, rather than measuring channel depths from between like 1 and 20 millimeters, we're going all the way up to 40 millimeters. And we did we sort of ran the analysis again with like a depth distribution that we know to be wrong. And it didn't really change connectivity. I think the caveat to that is that it could be because everything is so connected that like you couldn't change it that much more. But it would be interesting to sort of mess around with this in a less sandy system to see how wrong can you be about channel depth before it really starts to like make a difference to your architecture.
Yeah, definitely. Okay, our next question is from Gary, coming from London. He says, hi, Elizabeth, thanks for the great talk. Do you have a sense of how many plan view images or time steps you would need in a natural system to construct a meaningful stratigraphy?
Yeah, that's another really good question. So I think this is where like we would need, like in natural systems is where we really need to have a solid understanding of the kinematics to sort of like predict where these rivers are going in between these like big chunks of time steps. I think that you could, I guess if your question is referring to, oh, you do, it is a natural system. Yeah, I mean, I think it depends on how active these river systems are. This isn't a very satisfying answer because I don't really know the answer, but I think if you have highly mobile river networks, you're going to need a closer time step. And I think we're probably like even reaching the limits of like how much imagery we have going back in time. I mean, Google Earth Engine has a lot of excellent imagery, but again, it's still only a pretty limited time span. And so I think in natural systems, it's going to be a lot more important to not necessarily just take these plan view images, but to sort of combine them with maybe like modeling how we think these rivers, how realistically we think these rivers would move around through time. Sorry,
Yeah, that's an interesting question, and definitely interesting things to keep in mind as well. But it would be cool to get, if you guys could work out sort of a number or an idea that combines sort of mobility of the system and then figure something out for a given time frame. Yeah, you know, if you want 1,000 years or 2,000 years and the system is X% mobile, let's say.
Yeah, I mean, I think the thing that's kind of nice about this method is that it is like extremely fast. So if you just have some images, like you can just play around even with like, if you just want to assume like you have a certain set of network realizations and you just want to combine them a bunch of times and give it an aggregation rate. Like you could play around with the code and it's so fast to run, like, you know, less than a minute, that that there's a lot that you could sort of play around with and try to figure out like, okay, is this reasonable, or are we just like going way too far away from anything that's like based in reality at this
reality point? Right. I'd like to stay here, huh? Okay, our next question comes from Ross in Kingston, Canada. This is very interesting. Thank you. How did you choose the particle size distribution of the input sediment? Do you have a sense of how mud fractions might change the results?
Yeah, Ross, this is the question. So I was not around when this experiment was run, so I'm just using the data set. But a lot of the experiments done in the Jurassic tank and at SAFL use this mixture of quartz sand, I don't actually know the grain size, and coal, and they're basically mostly scaling, more than scaling the grain size distribution. There's a lot of scaling that happens with weight and sort of settling velocity. So the coal is simulating that fine grained sediment because it settles more slowly and behaves more like what we could imagine mud would be doing. The problem is, yeah, there's no cohesion. Like we don't have any cohesive component in this. There is sort of what we're planning on doing for our delta is using a mixture that's used at ExxonMobil for cohesive deltas that Kyle Straub was pretty helpful in sort of pointing us towards. And so we're sort of using that mixture, which has a whole range of different grain sizes, actually pretty coarse sand, all the way down to what's called ceramic microsphere, so like 11 micron particles. And then some cohesion is added by putting bentonite in. But then you have to put in another thing like some kind of polymer stabilizer to make it more cohesive. On it, like I'm sure there are people in the audience here who have more experience with this, but it's not that straightforward. Another thing that people do sometimes to create cohesion in the absence of like fine-grained sediment is they'll vegetate the delta. So they'll put alfalfa sprouts in the delta and they'll grow alfalfa. That's a little complicated because you have to like, it slows things down a lot because you have to like wait for them to grow and then they die and you have to reseed and things like that. So anyway, I think to get at your other question about changing the mud fraction, I think it would change the results a lot because it's going to change your mobility of your networks. So I don't think it changes the results in that. I think the method will hold still, it will still work, but it will change the mud fraction. I think it will make things more interesting, to be honest. I still think though that these sort of dynamics of like your floodplain aggregation rates changing during different sea level phases will hold, and that it will continue to be, you'll probably have more isolated sand bodies and it will continue to be harder for them to erode into underlying sand bodies if you've got these high aggregation rates.
Mhm. And the last part of his question just mentions that mudbeds can also be a good thing to protect underlying aquifers from contamination.
Yeah, yeah, exactly. So in this case, that's true. I, sort of originally came into this project from like an oil and gas mindset, thinking like, oh, we want all the fast flow pathways. But actually, in a lot of cases, like in this setting, the fast flow pathways mean transport of contaminants. So for sure, that's an important sort of piece of it.
Aspect, yeah. Okay, our next question comes from Ajit Singh from India. First question, he has two. Great presentation. How do these experiments look for alluvial fan systems close to mountains?
Yeah, I mean, these systems, like obviously in those cases, then you don't have these like sea level controls. There are some, I'm completely blanking on the authors now. There's an interesting paper that came out recently on distributary fluvial systems, an experimental paper, sort of looking at the barriers. And I think if I remember correctly, I feel bad because I can't remember who wrote it. I think if I remember correctly, they actually saw some differences. Like they found that their barriers got wider downstream, so they're not getting dissected. So that's kind of interesting. I'm not sure why they would be different. But this is actually pretty similar to alluvial fan settings where you have these braided distributary systems. You just wouldn't, I guess, have the sea level aspect of the picture.
Yep. Okay, they also wanted to know a little bit more about the experimental parameters, such as aggradation rate, sediment flux, and the material used in your experiments.
Yeah, so, oh gosh, I can't remember these exact values, I'm gonna be honest, but if you were to look at Hayek, I'll type it into here, Hayek et al. 2010, I can't remember even, that's not, oh wait, I think I just said that to Sense Online, sorry. But that has a lot of the information about sort of the experimental conditions. Or if you wanted to shoot me an email, I can look up those numbers and send them to you. I just don't have them off the top of my head right now.
Yeah, perfect. Our next question comes from Stephen in Wales. Could this system be adapted to look at ephemeral subaerial channel systems? He's thinking alluvial fans.
Yeah, I think so. I mean, really, like if the basic assumption holds, like if you are interested in basically knowing where the channels have been through time and you have some information about how it's aggrading, I think that it is pretty adaptable. So, here we're basically assuming like, and I know that obviously this is a simplification, but we're assuming sandy channels, muddy overbank. And so if similar like situations happen, or if you're just interested in knowing like where the different parts of the deposit are ending up, I think it could absolutely be used. I think the key is just knowing, like the key, which is not trivial, is knowing sort of how the network is moving through time.
Yeah, and he says thanks. He was just thinking that there might be a better chance in subaerial systems.
Yeah. Yeah, and they're quite active, right? So you can get like probably, the thing about these like big single thread river systems is that although they can be pretty active, they're not active on the same time scales that these subaerial fans are. So you probably have a better chance of like higher temporal resolution network changes.
Yeah, would make sense. Okay, our next question is from Valentine in Oslo. This is so awesome, Elizabeth. How much did the rivers incise in the substrate during the period of sea level fall?
Yeah, I think there are some places where if you look at the, actually, I'm gonna go back to my title. We can look here, I suppose. So I think if we jump to sea level fall, there's some places where you do see some like big incised valleys. Although it seems like nothing too huge. I think it only ended up in the end, this is just sort of a ballpark estimate, but I think it only ended up probably eroding like, I don't know, a couple of centimeters of material, but in this scale that's like pretty solid. I was just thinking there's like one, every time I see it, it looks like a big incised, So here you can see like there are edges here where we have like quite a lot of incision in the phases of sea level fall. So again, not a very quantitative answer, I guess, but it was enough to essentially be generally non-aggradational and slightly degradational.
Okay. Yeah, and he just explained a little bit more. I guess I'm asking if the experiment led to the creation of incised valleys. We got that. And if those incised valleys impacted the rate of avulsion of the channels, either as they were being created during forced regressions or after they were formed during transgressive phases.
Yeah, I think it'd be interesting. I think this is something that Austin's work is going to hopefully be able to show a little bit, because it's actually like really, even in experimental settings, it is not always that straightforward to identify avulsions versus sort of lateral migration. And so I think he's getting closer to being able to sort of quantify periods when avulsion is more dominant and when it isn't. Sort of generally what he's finding is these rivers, at least in this system, seem to widen through time and then kind of abandon and start over and widen through time. And so whether that changes during the big sea level fall would be pretty interesting. In general, these rivers do not seem to have any real challenges in like sort of migrating and getting across the surface. It seems like there's not really periods where it gets like locked into a valley in any real way.
Sure. Okay, if we don't have any more questions, Elizabeth, thank you so much for this wonderful presentation. I really enjoyed it. I hope everybody in the audience did as well, or I'm sure they did. And everybody out there in the ether, don't forget to join us next Wednesday for our next SEDS Online presentation, which will be from Lillian Navarro, and she's going to discuss channel lobe transition zones. And we'll see you then.